for the time at Graphite on Scale. Welcome.
Hello everybody. Today I'm not going to talk about products. We're going to talk about graphite instead and what we are doing with it at Criteo. So first, let me present myself. I'm working on graphite with the observability team at Criteo. And before that, I was working at Google on Untitled Chapter. So yes, like the two previous speakers, I was also working at Google, but it's not a conspiracy. Who here is running graphite in production? So still quite a few people are using it, and that might be useful for you. Or I might know some things that could be useful later. Today we're not going to talk about graphite, but about BigGraphite, which is what you may want to use when you have a lot of data. As you might have realized, graphite is a nice tool to use when you just want to get a few metrics from a few servers or applications. What it does well is, given a small or a set of metrics, you can browse metrics that you have and display graphs showing them. You can use graphene on top of it to build dashboards. Basically graphite. How does it work internally? It's important to dig into that to understand the rest later. Graphite is divided into two components. The first one is carbon. That's the application that you send metric to. So all of your applications or servers are periodically, like every minute, sending metrics to carbon, which will then persist them to disk. The default database for carbon is called Whisper. And with Whisper, each metric, so metric would be here, for example, was 123 CPU 0 user, plus then you have text value. So the metric is the first part, the name. So each metric in Whisper will be one file, which means that periodically your host is sending like 100 metrics, one for each CPU, plus memory and everything. Carbon will receive them over TCP, UDP, or other things if you want to, and write them to separate files. So that's what it does. You also have Carbon Relay and Carbon Aggregator that are used to do other things before Carbon Cache, which is the component that is writing to list. You can use that to, for example, duplicate the stream of metrics to different cluster. On the aggregator, you can use it to do a sum over 1 minute or some things like that. But we won't go into this exercise. So now you have an application that is sending metrics to Carbon and it's written to disk. How do you make a graph out of that? The component that does that is graphite-web. Graphite-web is basically a Django application that will read these files back from the file system and either display some JSON that you could use somewhere, like a graph to display graph, or directly a PNG that will be your graph. Graphite-web has a UI that you see when you use graphite, which is the metric tree on the graphing area. And it also has, more importantly, an API. The API has two main endpoints. The first one is the one that is used to find metrics, which is particularly useful when you want to autocomplete something, in Grafana, for example. The second one is the one that will get you points, the points that you asked. In this example, you asked for the sum of my.metric.wildcard in the last 10 minutes, and it will give you back the sum for all these metrics in the last 10 minutes. So that's graphite-web. And that's it. So how do we use graphite? We're pretty big, not as big as Google or Amazon, but still we have 6 data centers, 10 of thousands of servers and applications. We ingest quite a lot of metrics, so it's almost 1 million metrics now. We write 220k metrics per second, and we write 800k metrics per second. More importantly, when we tried to scale graphite, we already had thousands of existing dashboards and alerts. And that's something that was written by 30 teams, distributed over 2 continents. And you can't just say, okay, graphite doesn't work anymore, you will just switch to something else. That's impossible. So big constraints for us was, we need to fix graphite, and we'll see why, but we need to keep these dashboards and alerts working, and that's super important. So we've seen the two components of Graphite, and that's the overall architecture. If you have a simple setup, you will have just your application, Carbon, Graphite Web, and that's it. Since we're pretty big, we can't just do that. So what we've done is that in each data center, there are a few Carbon relays that are listening for points on EDP from every application in this data center, and then sending these points over the one to the main Graphite cluster. And this main Graphite cluster, there is again a relay that will distribute the points across multiple Carbon caches and write that to the database, which will then be read by graphite-web. So why do you want a centralized cluster? It's because when one of your users wants to see how one service is behaving, you don't want the user to go to 6 different UI or iframes, so you want to centralize everything in a single place, which makes things harder because you have a bigger cluster to take care of. Also, that's good on everything, but what do you do if one of your data center catches fire? Well, you just have the second data center. So what we do is that the Carbon relay that we have in every data center is just duplicating the traffic to 2 different data centers, and the user will just create any of these data centers that works currently. Yeah. So what's wrong with that? That's the architecture that we already had 1 year and a half ago, but it did not work so well for us. The software was working, but we were spending a lot of time trying to make it work for a lot of reasons. As we've seen, Whisper is writing 1 file per metric, but what do you do when you want to have 2 servers? You need to move some files somewhere else, merge them back, and everything. It's complicated. There are tools to do that, but it used to take us 1 week to do that, to add 1 server, and that's not a good use of time. The clustering at the time, it's better now, but at the time it was very naive. So let's imagine that you managed to shard all your data on 10 nodes, then one of them stops answering, and you have 500 for all your requests, because this one is not working. It's better now, but it used to be that, and that's not optimal, because the more nodes you have, the more likely to have you are to have one failing. And some queries that might look simple at the beginning will just overload all the nodes. And the thing that we have, as you've seen, that we had 2 different data centers, and sometime one of the link was down, and it was back up. We wanted to reconcile all the data so that the user will not see a gap that they will not see before. And the tooling to do that exists, but again, it will take up to 1 or 2 days to merge everything back, even on SSD and very big machines. So that worked, but we did not really like spending all our time working on that, on just starting scripts. And the thing is that most of these issues have been solved by actual distributed databases. If you look at Cassandra, at React, at HBase, at everything, they've all already solved these issues, so why should we try to do it again when people have done it better than us already? In most of these, you have application, you have program rates, you have a lot of tools, and you could just so the idea is that at the time I thought that we could just write the points to this database, get them back, and just be done with it. And most of them, we can just add 1 node, and the database will just, in the background, represents the data, and you won't see anything, and it will work. So that looked good, and that's why we started the BigGraphite project. What it is exactly? So, first, okay, databases have solved that already, but maybe there is somebody that had done that before with Graphite. And yeah, people have tried. And so, OpenTCP was another time-series database that we could have used, but there was no Graphite compatibility. We only have 1, even if it's big, we have a single HBase cluster at Criteo, and we want some kind of data center residency. There was schema, which also used Cassandra, but at the time used Elasticsearch, and we wanted to have to maintain only 1 database, not 2. Also, it did not exactly behave like the vanilla Graphite. And now, as we've seen before, thousands of dashboard layers, we want the exact same behavior. We don't want something to change. And schema is not a good option for us. FOSDEM claimed that there was compatibility, but again, it was not exact compatibility. And at the time, the project was using updated libraries, so it was not a good solution for future. And we looked at maybe 10 time-series databases, and we found nothing that could cover our needs. So we started working on something. So the goal was to get something like that. You get Carbon, again, to get metrics, and then you write to Cassandra, and then graphite-web will get metrics from Cassandra. And the idea is that once one of the components becomes overloaded, we just want to be able to increase the number of instances without having to do anything more. So let's say that's, what does it work? Yeah. So let's say that we need more UI because a lot of people are doing queries on an event is cached, which is using a lot of CPU there. You can just add one more UI or one more graphite-web, or a new Cassandra node, a new carbon cache, yet another Cassandra node. And the idea is that for the operator, you will just add a machine and that's it. You don't deal with the weekly rebalancing stuff. So that's the idea. How do you do that? How do you change Graphite database to use Cassandra? The good thing is that Graphite 1.0 came with plugins. On writing plugins for Graphite is not super hard. On Carbon, you just need to support basically two operations, or three operations. One to check if the metric exists already in the database. Another one to create the metric if it doesn't. And the last one to add data points in the database. So basically you have a Python class where you need to implement these three methods. And for graphite-web, you need to implement two things. The first one is to be able to find a list of metrics based on the glob. So let's say that the user wants my.metric.wildcard. You need to return the list of metrics that match that. And the second one is given one metric on a time window, return the points for this metric. And then Graphite will take off all the rest. So, sounds simple, right? You just need to implement this thing, and then you have Graphite on whatever, on Cassandra for us. So, yeah, what I said, you need to store two things in your database. The points. The points are tuples of timestamp and value being doubles. But there is a small complication. You need to store these points at multiple resolution. You could store 1 point per second for 1 year, but that will take a lot of space. So what we do instead is that we store 1 point per minute for 1 week, then 1 per hour for 1 month, and then 1 per day for 1 year. On this way, people can have long-term data, and it doesn't end up costing 1 petabyte of disk. So that's the right path. You get points, you write them. On the read path, you get a metric, a time window, and your autonomy set point. It's important to optimize the storage for the read path, which is not exactly, as Brian said before, the same pattern as when you write. The other thing that you need to do is to store metric names to be able to browse there. And it's not only the metric names, it's also the metadata that you associate with metrics. So like the resolution, when was the last time you wrote to this metric, you write from it, and that kind of things, which are useful. So we decided to go with Cassandra because we already had Cassandra too, but we could have done that with React or any other database. But Cassandra worked well for us. And now I will try to explain how you can do that with Cassandra. And it's not as simple as you would think. So for points, the main thing that you store in a time series database is a point. It would be something simple, right? You could just have one table where you store a metric and a list of points. In Cassandra, that would be something like that. The partition key would be the metric. Then you would have the timestamp, which is the clustering key, and then all the values. That works if you don't have a lot of points for the same metric, and if you don't try to expire all the points. because if you try that, then you will have a lot of tombstones or everything. I won't describe that here now. But basically, that would have ended up just breaking after 1 year, and we didn't want that. So we did something that is slightly more complicated, but still not too bad. What we are doing is that instead of having one line per metric, we divide the points in blocks, kind of like Prometheus, where we divide in blocks of 2 hours. We do that. We have something that we can configure, and we do one line with a certain duration of points, and we just create a new line after that, and yet another new line, which allows us, when we want to remove all points, just to remove the whole line completely, and not to remove cells inside this line, which is more efficient. Another thing that we do is that we have one table per resolution, which allows us to put some specific settings, for example, for the points from today, we want to cache them more, and for the points for the last year, we might want to put them on a slower disk or something, or to use another kind of compression. So we have one table per resolution type. And in the end, it looks like this. You have the metric, which is here already, because you don't want to repeat the metric name all over the database. You have the start of the block, the offset within the block, and all the values. And that works pretty well. It's even more complicated than that when you want to add aggregation and you want to have multiple cluster writing to the same database, but that's the idea. So that's for points. That's fixed. We know to write, we know to read. Let me go back. So when you write, you just add one line at the end, and when you read, you select the metric, the block that you want, and the range of offsets that you want inside that block, and that gives you a point that you want. But as you might remember, the plugin system of Graphite also asks you to return the metrics matching one block. And for that, you need an index somewhere. Basically, what you're allowed to do with Graphite is, so you have components that are separated by points, and you're allowed to put wildcards on other things. For example, if you do fish.star.nemo.star, you would match fish.something.nemo.foo, and you need to have an index where you can do that kind of thing. Looks easy, but when you have 100 million metrics, that's probably 10 gigabytes or something, you can just do grep inside the file. You need to do something smarter. The first idea was to use Elasticsearch. That would have worked well, and as a matter of fact, we have tools in the repository to import all the metrics in Elasticsearch. But it was hard enough to migrate to one database that we didn't want to learn how to use two of them, so we tried to do that in Cassandra directly. Cassandra is not the best database for indexes, but it has some support for them. Starting with 3.5, you have SASE, which is a secondary attached, assistable attached secondary indexes, which allows you to index some columns and to prefix searches in these columns, which was enough for us. What we've done is that given a path, let's say Cassandra.Criteo.uptime, we will just split this path into components. So in this example, the first component will be Criteo, second one will be Cassandra, third one will be uptime, and we will mark the end. The fourth one will be end marker. You can do that, or you can just store the length of the metric, but it's easier to do it this way. So we split it into components in the table, and then we index each of them individually, which means that if somebody wants to look for 3.star, they just look for any column where the component 0 is equal to Criteo. And because the length must be 2, where the component 2 is the end marker. And that's as simple as that. And then you just express constraints on all the indexes, and Cassandra will return you the intersections of all these constraints. You can learn more about that in the design doc that is here on how SASE indexes work. So more example about that. For a simple metric, which is predefined, you can do that. Just express the constraints of every component. That will be stupid because since the metric can also be a partition key, you can create directly on that. But for others, with stars, as we've seen before, you just exclude the one where you don't know what would be there. So if it's a white card, you don't add something on it in the query. And that will give you the results. The thing is that Graphite does not only support wildcards, it supports other things like braces, or it can be one of these characters, or it could be characters from 0 to 9, or any character. And Sassy doesn't support that. So what we've done at the time is that each time it will be too complicated, we would just replace the complicated thing by a prefix, if possible. So let's look at the first component, it's match. It's either matched by or matching. And here we will do select where part 0 starts with match, and ignore the rest, and do that as a post filter. It's not super efficient, but it works well enough at the beginning. Later, what we did is that in this case, we will just expand the brace, and instead of running one query where it starts with match, we'll say, okay, let's do one where it's matched by, and another when it's matching, and run both in parallel. And that's the second thing that we've done. And yeah, it worked pretty well. So as long as we had, I think it was 50 million metrics, that worked well. After that, it stopped working so well, and we sometimes spend multiple seconds finding metrics. It's not that long, but when you have 100 graphs to display, and each of them is taking 5 seconds, that's not really optimal. So what we've done lately is that instead of using Sassy, we're using Lucene in Cassandra instead, and just converting this expression into a Lucene expression and letting Lucene do what it knows how to do. So we're still not using Elasticsearch. We don't need to deal with another database, but we have a better indexing engine. And that's it for Cassandra. And then, so what can you do with it? So, yeah, we wrote that. It took us almost 1 year. And then we deployed it. And so now all the graphite clusters at Criteo are running with BigGraphite. It's pretty big. We have a lot of capacity, and we are not using it all yet. It's absorbing 1 million points per second on 10K read per second, which is a lot. What it's not yet good for is efficiency. We still have 16 bytes per point after compression. Mostly because we did not try to optimize that yet. As you can remember, the most pressing point for us is not to lose 1 week to add 1 node. And that worked because here you can see that we are using 20 Cassandra nodes per cluster. And at some point we realized that we partitioned wrongly the disk. We just wrote a new chef recipe, deployed it, it reinstalled all the machines one by one, and we had nothing to do. Which was pretty nice, instead of having to spend 20 weeks to realize everything. We don't have 2 clusters anymore, we have 3. Because let's imagine that somebody is by mistake doing dark key space on the Cassandra cluster, we will lose everything because it's replicated. So we have 2 replicated clusters on one that is isolated, that we use as a fallback if something really wrong happens to the 2 others. And how can you use it? And it's pretty simple actually. You just pip install BigGraphite, create the schema, import the data from Whisper, set the storage fader to BigGraphite in both graphite-web and Carbon, and you're done. That's not the most efficient to convert your Whisper-based cluster to BigGraphite-1, but what you can do on top of that is just write to Cassandra, but read from both Cassandra and Whisper. There is a plugin that is BigGraphite plus Whisper that you can use, and it will just merge the 2, and you can just do that, and then import in the background the data. And as soon as you're done, remove the Whisper files, and it will go to Cassandra. So it's pretty easy to use it. Some links that you can use, that you can read later if you want to know more. What's most interesting here is the design doc that we've written at the beginning, before doing the project, that explains how it works and why we did things this way. Roadmap. What should we do? Yeah, I'm talking Prometheus here. We use Prometheus too, and we want our user to use either Graphite or Prometheus, but to be able to find their Prometheus metrics in Graphite and vice versa. So we built a tool which is called the Graphite metadata that will just write metrics from Prometheus to Graphite and allow Prometheus to read back from Graphite these metrics. So it's kind of transparent for users. And we want to optimize writes. Basically, what Brian said before, you need a big write buffer. We don't have it currently because if we add it, it will increase the delay between the ingestion of points and the time where user can read it. And we need to work on that. We could do it, but it will take 3 minutes for a point to arrive. But we'll also divide the CPU usage by 3, which is not that bad. And we need to optimize the rate, but it works pretty well. Just a thing that might be interesting because it's still a monitoring talk. How do you make sure that you are monitoring? So we rolled out a new graphite system and we wanted to make sure that it worked. What are you supposed to do to make sure that it works? So we did two things. Two things per component. For graphite-web, we periodically, every minute, send one query, try to fetch metrics, and we see if it succeeds or not. That's the read availability on the top left. And we also store the latency for the read path. On the write path, every minute we send points from every data center, and we check that they arrive correctly, and if they don't, we mark them as loss. So we get the percentage of points that we are losing. We also use the timestamp as the value of these points, and we can find how long it takes for one point to get into the database, and that's what is in the right button, which is the time it takes to reach the database. So that's the SLA that we have, and basically we target like 99% availability over 10 minutes. I think 1 second of latency, we don't want to lose too many points, so I think 0.5% of the points lost. And the delay for the target delay is probably 2 minutes. After that, we get a page. Yeah. Any question?
So thank you very much. We have 3 minutes left, so please stay seated and be quiet so that we can hear the questions and answers. First, thanks very much for that presentation. Really cool with using graphite again, which once was available and then didn't work. I just wanted to know, did you take a look at the stuff the guys from Booking.com did, like the carbon C relay and the carbon silver and all that stuff?
So we talked to them, and when we talked to them, it looked like what they did has a lot of dependencies and did not behave exactly like vanilla graphite, so we did not go with it. But if you don't have as many as existing dashboard as we do, that's probably something that works for you. And I think RainTank also have another solution, metric tank, that works well, but it doesn't behave exactly like vanilla graphite.
Hello. So I have one question. You mentioned 20 terabytes of data points, which seems amazing. The first question is how many distinct time series that represent? And do you have any way of quantifying how many time series are written but never read a single time?
So yeah, that's 20 terabytes before application. It's more like 80 because we replicate a lot, well, 4 times. And that's 100 million time series. And we do know which ones are being used because we mark the last time the time series was read. So each time there is a read, no. Sometimes we mark it because you don't want to do it every time you read, but we do mark that, and we have the timestamp, this timestamp. So we are not doing the stats yet, but we could do them, and we could try to maybe some advise teams to stop sending these metrics because they are useless.